Imagine a simple experiment. Tiny particles, like electrons, are fired one by one toward a barrier with two slits. Behind the barrier, a screen records where they land. Common sense tells us they should pass through one slit or the other, creating two distinct bands on the screen. But reality has other plans. Instead, an interference pattern emerges as if each particle is passing through both slits at once, like a wave. But here's where it gets stranger. When scientists try to observe which slit the particle goes through, the interference pattern vanishes. The particles suddenly behave like tiny bullets again. It's as if reality knows it's being watched and changes its behavior accordingly. This is the famous double-slit experiment, first performed in the early 1800s with light and later with electrons. At its core, it reveals a fundamental truth about quantum mechanics. Particles exist in a state of superposition, meaning they can be in multiple places at once until they are measured. Think of it like a spinning coin. While it's in the air, it's neither heads nor tails but both simultaneously. Only when it lands, when it's observed, does it settle into one state. The double-slit experiment suggests that reality itself is fluid until we look at it. What does this mean for our understanding of reality? If particles behave differently when observed, does consciousness play a role in shaping the universe? Some interpretations of quantum mechanics, like the Copenhagen interpretation, suggest that observation collapses the wave function, forcing reality to choose a definite state. Others, like the many worlds interpretation, propose that every possible outcome happens in a branching multiverse. This experiment forces us to question whether the universe exists independently of us or if our perception somehow molds it. Are we merely observers, or are we participants in the creation of reality itself? If the double-slit experiment makes you question the nature of reality, then our next mystery will take you even deeper. What if every possible outcome does happen just in parallel universes? Let's explore the mind-bending implications of the many worlds interpretation. Imagine a moment in your life when you made a crucial decision. What if, somewhere out there, another version of you took the opposite path? What if every possible choice you could have made actually happened just in a different universe? This isn't science fiction. It's the many worlds interpretation of quantum mechanics, a theory that suggests reality constantly splits into infinite parallel timelines. Every quantum event, every decision, every random fluctuation spawns a new universe where each possibility plays out. Proposed by physicist Hugh Everett in 1957, the many worlds interpretation offers a radical solution to the measurement problem in quantum mechanics. Unlike the Copenhagen interpretation, which says observation collapses probabilities into a single outcome, many worlds suggest that all outcomes occur each in its own branching reality. Think of it like a choose-your-own-adventure book where every possible choice leads to a new story. In one universe you took that job offer. In another you moved to a different country. In yet another you never existed at all. If this is true, then somewhere out there, every conceivable version of history is unfolding. A version of you is a famous artist. Another is an astronaut. Another never left their hometown. The implications are staggering. Free will, destiny, and identity all take on new meanings. But how could we ever prove this? Some physicists suggest that quantum decoherence prevents us from perceiving these alternate realities. Others argue that the many worlds interpretation is untestable, making it more philosophy than science. Yet, it remains one of the most compelling explanations for quantum behavior. If reality is constantly splitting into infinite versions of itself, then what does that say about time? Is the past just as fluid as the future? Next, we'll explore the block universe theory, where time may be nothing more than an illusion. Close your eyes and think about the past. A childhood memory, perhaps vivid, real, as if it's still happening somewhere. Now think of the future, uncertain, unwritten, yet somehow already out there, waiting. What if the distinction between past, present, and future is nothing more than a trick of the mind? What if time, as we experience it, is an illusion and reality is more like a frozen block where every moment exists simultaneously? This is the block universe theory, a radical idea in physics that suggests time doesn't flow at all. Instead, the past, present, and future are all equally real, laid out like frames in an endless cosmic film. Einstein's theory of relativity shattered the Newtonian idea of absolute time. According to relativity, time is interwoven with space into a single fabric spacetime, and it can stretch, bend, and even slow down depending on gravity and motion. The block universe takes this further. Imagine the entire history of the universe from the Big Bang to the heat death of everything as a four-dimensional block. Every event, every moment, exists eternally within it. Your birth, your death, the rise and fall of civilizations, they are all fixed points in this unchanging structure. Think of it like a DVD. The movie is already complete, every scene exists on the disc. But when you press play, your consciousness moves through it, creating the illusion of time passing. If the block universe is real, then free will becomes a haunting question. Are our choices truly ours, or are they predetermined, already etched into spacetime? Some argue that our perception of now is just a psychological construct, a way for our brains to make sense of reality. Even more unsettling, if time is an illusion, then death may not be an end, just another point in the block. In a sense, we are always alive somewhere in spacetime, frozen in moments of joy, sorrow, love forever. Does this mean the future is already written? Or is the block universe just a mathematical model, not a true description of reality? The debate continues, but one thing is certain. Time is far stranger than we think. If time is an illusion, then what about cause and effect? Can the future influence the past? Next, we'll explore quantum retrocausality, where the arrow of time may not be so rigid after all. We've all heard the saying, you can't change the past. But in the quantum world, the rules are different. What if events in the future could ripple backward, influencing what happens now? What if some particles already know what choices we'll make before we make them? This isn't science fiction, it's quantum retrocausality, a controversial idea suggesting that under certain conditions, effects can precede their causes. In classical physics, causality is sacred. Cause comes first, effect follows. But in quantum mechanics, particles can become entangled, meaning their states are linked regardless of distance. Some interpretations suggest that measuring one particle now can instantaneously affect its partner, even if that partner's measurement happens in the future. Imagine sending a letter to your past self. Normally that's impossible. But in quantum terms, it's as if a decision you make tomorrow could subtly alter the behavior of a particle today. Experiments like the delayed choice quantum eraser hint at this. In these tests, a particle's behavior seems to change based on a future measurement, as if it's aware of what's coming. If retrocausality is real, it could rewrite our understanding of time. Perhaps the universe isn't strictly linear, maybe the past and future are in a constant dialogue, shaping each other in ways we don't yet understand. Some physicists argue this could explain quantum weirdness without invoking parallel universes. Others say it's just a quirk of math, not real physics. But if true, it means our actions today might be influenced by events that haven't happened yet. Does this mean destiny is pulling the strings? Or is reality far more fluid than we imagine? If time can bend backward, then what about information? Can anything truly be erased? Next, we'll dive into the black hole information paradox, where even the laws of physics seem to break down. Imagine throwing a book into a fire. The pages burn, the ink fades, but in theory, if you could track every atom and energy fluctuation, you could reconstruct its contents. Now imagine throwing that book into a black hole. According to Einstein's general relativity, it's gone forever, crushed into a singularity where even the laws of physics break down. But quantum mechanics insists that information can never truly be destroyed. This contradiction between relativity's unforgiving black holes and quantum theory's preservation of information is one of the greatest unsolved problems in physics. The black hole information paradox. Black holes, as predicted by general relativity, are regions of spacetime where gravity is so strong that nothing, not even light, can escape. Anything that crosses the event horizon is lost forever, compressed into an infinitely dense singularity. But quantum mechanics has a fundamental rule, unitarity, which states that the total information in a system must always be conserved. Just as you could, in theory, reverse a scrambled egg if you tracked every particle, quantum theory suggests that information swallowed by a black hole can't just vanish. Stephen Hawking discovered that black holes aren't completely black, they slowly evaporate over eons, emitting Hawking radiation. But here's the problem. This radiation appears to be completely random, carrying no information about what fell in. So where does the original information go? The black hole information paradox strikes at the very heart of physics, forcing us to question whether our most fundamental theories about reality might be fundamentally incomplete. If information truly vanishes in black holes, it would mean quantum mechanics, with its sacred principle that information can never be destroyed, is wrong in extreme cosmic environments. This would require nothing less than a complete rewriting of our understanding of the quantum world, potentially unraveling decades of established science. Yet if information somehow survives, the implications are equally staggering. The holographic principle suggests that all the information swallowed by a black hole might be encoded on its two-dimensional event horizon, like a cosmic fingerprint preserved in Hawking radiation. This would mean our three-dimensional reality could be a projection of information stored on some distant, invisible surface, a concept so alien it challenges our most basic perceptions of space and dimensionality. Even more radical is the firewall hypothesis, which posits that the event horizon might not be the smooth gateway predicted by relativity, but rather a searing wall of energy that vaporizes anything crossing it. While this would preserve information, it would also mean that the peaceful fall into a black hole imagined by Einstein's equations is impossible. Instead, you'd be annihilated in an instant, your information scrambled into quantum noise. Perhaps the most mind-bending resolution suggests that black holes might birth new universes, with the swallowed information becoming the seeds of an entirely new spacetime continuum. In this view, every black hole in our universe could be the Big Bang of another, making our entire cosmos potentially just one link in an infinite chain of universe reproduction. This paradox does more than challenge specific theories. It forces us to confront whether our current frameworks can ever truly describe the most extreme phenomena in nature. The very concept of information itself may need redefinition in the violent physics of black hole evaporation. As we continue probing this mystery, we're not just studying distant cosmic objects, we're testing the limits of human understanding itself. If black holes can warp the fundamental nature of information, what about particles that defy our understanding of time and space altogether? Next, we'll examine the enigmatic possibility of tachyons, hypothetical particles that might move faster than light and backward through time. Light speed is the universe's ultimate speed limit, or so we thought. But lurking in the equations of relativity is a strange possibility: particles that always travel faster than light. These hypothetical entities, called tachyons, don't just break the cosmic speed limit, they might also move backward in time. Are tachyons real, or just a mathematical oddity? And if they exist, what would that mean for cause and effect? Einstein's theory of relativity states that nothing with mass can reach or exceed the speed of light. Doing so would require infinite energy. But tachyons, by definition, always travel faster than light. Unlike ordinary particles, which slow down as they gain energy, tachyons would speed up as they lose energy. If they lost all energy, they'd hit infinite speed, a concept that makes no physical sense, suggesting tachyons might be impossible. Yet they remain a fascinating what if. Some theories suggest tachyons could be time-reversed particles, appearing to move backward through time from our perspective. If tachyons were real, their existence would unravel the very fabric of causality as we know it. Imagine a particle that doesn't just break the cosmic speed limit but inverts the relationship between energy and motion. Unlike ordinary matter, which requires infinite energy to approach light speed, a tachyon would exhibit the opposite behavior. The less energy it has, the faster it moves. At zero energy, its speed would become infinite, a nonsensical proposition that suggests tachyons may be fundamentally incompatible with our universe. Yet, the theoretical possibility lingers, and with it, staggering implications. For one, tachyons could violate causality in the most literal sense. If you could send a message using tachyons, it might arrive at its destination before you send it, creating paradoxes that defy logic. Picture a scientist transmitting a tachyon signal warning their past self not to conduct the experiment that would have led to the discovery of tachyons in the first place. Would the signal ever exist? Could the past be rewritten, or would reality simply refuse to allow such contradictions, rendering tachyons impossible by default? Beyond time travel, tachyons have been floated as a potential explanation for dark matter, the elusive, invisible substance that makes up most of the universe's mass. If tachyons exist, they would be inherently undetectable by conventional means, moving too quickly to interact with light or ordinary matter. Perhaps they permeate the cosmos, their faster-than-light nature making them the hidden scaffolding of reality. But the most profound implication is what tachyons would mean for Einstein's relativity. The theory is built on the premise that light speed is the ultimate barrier, a cosmic speed limit woven into the fabric of spacetime. If tachyons exist, relativity would either need radical revision, or we'd have to accept that our understanding of physics is incomplete, that there are layers to reality where the rules we take as absolute simply don't apply. So far, no experiment has detected a tachyon, and most physicists consider them mathematical phantoms, curiosities that emerge from equations but have no physical reality. Yet the fact that they can be imagined, that the math allows for their existence at all, forces us to confront how little we truly know about the deeper workings of the universe. If tachyons challenge our grasp of time and motion, then what about the nature of existence itself? Could the universe be nothing more than lines of code in an unfathomable cosmic computer? Next, we'll delve into the simulation hypothesis, where reality itself may be an illusion. What if everything around you, the screen you're reading this on, the sensation of your breath, the vast expanse of the cosmos itself, was nothing more than an elaborate simulation? This is not the plot of a science fiction novel, but a serious philosophical argument gaining traction among technologists and physicists alike: the simulation hypothesis. At its core, this idea suggests that our perceived reality may be an artificial construct, an immensely sophisticated virtual reality created by an advanced civilization. The concept feels both ancient and cutting-edge, echoing philosophical questions posed by Plato's allegory of the cave while intersecting with modern computing and quantum theory. If future civilizations could achieve computational power vast enough to simulate conscious beings, how could we ever prove we're not among them? The modern argument for the simulation hypothesis stems from three unsettling premises. First, the exponential growth of computing power suggests that future civilizations could possess technology capable of running universe-scale simulations. Second, if such simulations are possible, there would likely be countless iterations of them, meaning simulated realities would vastly outnumber base reality. Statistically, we'd more likely be in one of the simulations. Third, glitches or limits in physics like the pixelation of reality at quantum scales, or the hard speed limit of light could be interpreted as processing constraints of the simulation. Philosopher Nick Bostrom formalized this reasoning in his seminal 2003 paper, arguing that at least one of these must be true. Either civilizations never reach technological maturity, they choose not to run ancestor simulations, or we are almost certainly living in one. The eerie possibility? The first two options seem unlikely given humanity's trajectory. If we inhabit a simulation, the nature of existence unravels into existential vertigo. The laws of physics become mere programming rules, subject to updates or overrides. Death might be a logout rather than an end. Religious concepts of creators take on startling new meanings. Our gods could be programmers. Even time itself may be non-fundamental, just a variable in a cosmic rendering engine. Some scientists have proposed experiments to test the hypothesis. One approach looks for compression artifacts, in reality like repeating patterns in cosmic rays that suggest a finite resolution to spacetime. Others suggest quantum indeterminacy could reflect processing optimizations, where unobserved phenomena remain unrendered to save resources. Yet the hypothesis resists definitive proof. Even if we found evidence of code, it could simply be a deeper layer of reality rather than proof of simulation. This leads to a profound irony. The more convincingly the universe behaves like a perfect simulation, the less distinguishable it becomes from a genuine reality. If reality might be a construct, then what constructs it? At the smallest scales, the universe behaves in ways that challenge all notions of solidity. Next, we'll probe the quantum foam, a seething, chaotic foundation to spacetime itself. Imagine zooming in on the smooth surface of reality past atoms, past subatomic particles, down to scales so infinitesimal that spacetime itself ceases to be stable. Here, at the very foundations of existence, the universe does not appear as an orderly void, but as a seething, frothing ocean of energy. This is quantum foam, a turbulent state of spacetime predicted by quantum mechanics where the very concepts of here and now lose all meaning. The notion seems almost mythological, a primordial chaos lurking beneath the illusion of solidity. Yet this isn't poetry, it's the consequence of marrying quantum theory with gravity, where the rules of the very large collide with the rules of the very small. In this domain, reality itself flickers in and out of existence, as fleeting as bubbles in a boiling pot. Quantum foam emerges from the Heisenberg uncertainty principle taken to its extreme. At scales of around 10 to the power of -35 meters, the Planck length, the energy fluctuations are so violent that spacetime cannot maintain its smooth continuity. Instead, it becomes a probabilistic storm of virtual particles, wormholes, and microscopic black holes appearing and vanishing in spans of 10 to the power of -43 seconds, Planck time. These aren't mere mathematical abstractions, they represent moments when gravity becomes so intense that spacetime loses its structure entirely, warping into a foam-like consistency. The concept was first proposed by physicist John Wheeler in the 1950s, who envisioned spacetime not as an empty stage, but as a dynamic, ever-changing medium. On cosmic scales, these fluctuations average out into the stable universe we perceive. But at the Planck scale, spacetime resembles an endless cascade of quantum bubbles, each a temporary distortion of geometry itself. The existence of quantum foam would fundamentally alter our understanding of reality's architecture. It suggests that the vacuum of space is not truly empty, but a fermenting sea of potentiality, a place where particles borrow energy from nothingness, where universes might spontaneously nucleate like droplets in a mist. Some theories even propose that our entire cosmos could have emerged from such a quantum fluctuation, a single bubble in an infinite foam of possibilities. This turbulence may also hold the key to unifying quantum mechanics with general relativity. In quantum foam, the smooth curves of Einstein's spacetime dissolve into probabilistic chaos, hinting at a deeper theory where gravity and quantum forces are two faces of the same phenomenon. Yet probing this foam directly remains impossible with current technology. The energies required are trillions of times beyond what our particle accelerators can produce. Perhaps most unsettling is the philosophical implication that solidity and permanence are illusions. The chair you sit on, the stars overhead, all are built upon this writhing foundation, their stability a statistical mirage. Quantum foam reminds us that at its core, reality is restless, unpredictable, and far stranger than our senses can comprehend. If spacetime itself is a turbulent sea, what happens when its waves grow violent? Next, we'll confront gravitational waves, ripples in the fabric of reality that carry echoes of cosmic collisions. Imagine the cosmos not as a silent void, but as a vast, resonating chamber, one where collisions between black holes send ripples through the fabric of spacetime itself, where the death spiral of neutron stars hums across billions of light years. These are gravitational waves, the cosmic vibrations predicted by Einstein a century ago but only confirmed in our time. They are not waves of sound or light, but something far more fundamental: the stretching and squeezing of reality itself as it responds to the most violent events in the universe. For millennia we observed the heavens through light alone. But gravitational waves have given us an entirely new sense, allowing us to hear the universe for the first time, to detect cosmic phenomena that emit no radiation at all. In their subtle tremors, we find proof that spacetime is not a static stage, but a dynamic, elastic medium that remembers every disturbance. Einstein's theory of general relativity revealed that massive objects warp spacetime around them. When these objects accelerate, especially in catastrophic events like black hole mergers, they create propagating distortions that travel outward at light speed. These are gravitational waves, incredibly faint undulations that alternately stretch and compress space itself as they pass. Detecting them required one of the most precise experiments in history. Facilities like LIGO, Laser Interferometer Gravitational Wave Observatory, use lasers traveling down 4-kilometer vacuum tunnels to measure changes in length smaller than 1,000th the width of a proton. The first confirmed detection in 2015 came from two black holes, each about 30 times the mass of our Sun, colliding 1.3 billion years ago. In their final moments, they radiated more power in gravitational waves than all the stars in the observable universe combined, yet by the time those waves reached Earth, they distorted our detectors by less than the width of an atomic nucleus. Gravitational waves have opened an entirely new window on the cosmos. Where telescopes see only light, gravitational wave observatories can hear the invisible black holes orbiting in perfect darkness, the internal structure of neutron stars, even potential echoes from the Big Bang itself. They may help us detect cosmic strings, hypothetical defects in spacetime left over from the universe's birth, or reveal whether our understanding of gravity holds true in the most extreme environments. These waves also carry profound philosophical weight. Each detection is a message from an ancient, violent past, a time capsule from events that occurred before multicellular life existed on Earth. The black holes whose merger we detected in 2015 had already collided and formed a new singularity 800 million years before Earth's first complex cells evolved. In their waves, we touch events so remote that by comparison the dinosaurs seem like yesterday. Perhaps most remarkably, gravitational waves prove that spacetime has a kind of memory. Every cataclysm, every collision leaves its imprint on the universe's fabric, an eternal, if fading, whisper of what once was. We are only beginning to listen to this cosmic symphony, and already it has rewritten our understanding of the heavens. If spacetime can ripple like a pond, could it also tear? Next, we'll explore wormholes, hypothetical tunnels through the universe's fabric that could bend not just space, but the very nature of possibility. Picture the universe not as a vast, empty expanse, but as a folded piece of paper where two distant points touch, separated only by the thin barrier of dimensionality itself. This is the essence of a wormhole, a hypothetical tunnel through spacetime that could connect otherwise impossible distances in an instant. Black holes swallow matter irrevocably, but wormholes offer something far stranger, a doorway that might link different locations, different times, or even different universes. The concept has fueled science fiction for generations, but its origins lie in the cold mathematics of general relativity. Einstein himself, working with physicist Nathan Rosen, discovered that his equations permitted such structures, leading to their original name, Einstein-Rosen bridges. Yet decades later, we still don't know if they exist, or whether they're merely tantalizing ghosts in the equations of physicists. A wormhole is, in essence, a shortcut through the warped geometry of spacetime. Imagine space as a two-dimensional sheet, bent so that 2 points nearly touch. A wormhole would be like a needle punching through that fold, creating a tunnel between them. In theory, such a structure could allow near-instantaneous travel across cosmic distances or even between moments in time. General relativity permits such solutions, but with staggering caveats. A traversable wormhole would require two things we've never observed: exotic matter with negative energy to prop open its throat, and an unfathomably stable configuration to prevent collapse the instant anything enters. The exotic matter alone defies known physics. It would need to exert negative pressure, effectively anti-gravity, to counteract the wormhole's tendency to pinch shut. If wormholes exist, they would rewrite not just physics but the nature of reality itself. Interstellar travel would become plausible without breaking light speed's limit. You'd simply go around the barrier. Time travel emerges as a disturbing possibility. A wormhole with one end moving near light speed could create a bridge between different eras, though the paradoxes this introduces might make such structures inherently unstable. Some theories suggest wormholes could be primordial, left over from the universe's birth, when quantum foam fluctuations might have birthed microscopic tunnels that later inflated to macroscopic sizes. Others propose that advanced civilizations could engineer them, though the energy requirements would dwarf anything humanity has ever produced. Most radically, wormholes might not just connect locations in our universe. They could be gateways to entirely separate cosmic realms, branches of the multiverse where physical constants differ, or where time flows backward. The philosophical implications are dizzying. If such structures exist, even fleetingly, the universe may be far more interconnected than we ever imagined. Yet for all their theoretical intrigue, no evidence for wormholes has ever been found. They may be mathematical phantoms, or they may be hiding in plain sight, disguised as black holes or lurking in the quantum foam. Until we detect one, they remain the most alluring what-if in theoretical physics. If spacetime can be punctured by tunnels, what other structures might lurk in its geometry? Next, we'll examine cosmic strings, one-dimensional scars from the birth of the universe that could warp reality around them. The early universe was a place of unimaginable violence, a seething cauldron of energy where the fundamental forces wrestled for dominance. As the cosmos expanded and cooled, it may have left behind scars, defects in the very structure of spacetime itself. Among the most intriguing of these relics are cosmic strings, hypothetical one-dimensional cracks in reality that could stretch across the entire universe. These aren't mere abstract curiosities, they would be filaments of pure spacetime curvature, so dense that a single inch of string might outweigh entire mountain ranges. Their existence would mean our universe still bears the wounds of its creation. Cosmic strings are theorized to have formed during symmetry-breaking phase transitions in the early universe, when the fundamental forces separated from their primordial unity. Picture the surface of water freezing as ice crystals form, imperfections develop at their boundaries. On a cosmic scale, such imperfections could have manifested as incredibly thin, just one Planck length across, but unimaginably dense filaments of trapped energy, stretching across billions of light years. Unlike black holes which curve spacetime into a pit, cosmic strings would create a distinctive angular defect in spacetime, a wedge missing from the cosmic pie that would cause light to bend around them in peculiar ways. These structures would possess extraordinary properties. A cosmic string under tension would vibrate at nearly light speed, potentially emitting bursts of gravitational waves. If two strings crossed, they might reconnect in explosive events called cusps, that could briefly outshine entire galaxies. Some theories even suggest certain string configurations could form time loops, regions where spacetime folds back on itself. Yet despite their theoretical might, cosmic strings would be nearly invisible, detectable only through their subtle warping of background light or their gravitational wave signatures. The potential discovery of cosmic strings would revolutionize our understanding of both cosmology and fundamental physics. They would serve as direct probes into the universe's first moments, carrying information about energies a trillion times beyond what our particle accelerators can reach. Their gravitational effects might explain some observed anomalies in galaxy distributions, and their vibrations could account for certain unexplained patterns in the cosmic microwave background. More profoundly, cosmic strings would demonstrate that the universe preserves its history in spacetime itself, that the violent processes of creation left permanent marks on reality's fabric. Some models suggest networks of strings could have provided the gravitational seeds for galaxy formation, meaning these relics may have played a crucial role in creating the cosmic structures we see today. Their existence would confirm that the universe underwent dramatic phase transitions as it cooled, validating key predictions of grand unified theories. Yet cosmic strings also present mysteries. If they exist, why haven't we detected their distinctive signatures? Are they too rare, or have we been looking for the wrong evidence? Some physicists propose that strings may have mostly decayed through gravitational radiation over cosmic time, leaving only faint echoes of their once dominant presence. Others suggest we might find microscopic cosmic strings in particle accelerator experiments if we could achieve sufficiently high energies to recreate the conditions of the early universe. If the universe can preserve its birth defects in spacetime itself, what other relics might be hidden in the void? Next, we'll examine magnetic monopoles, theoretical particles that could rewrite our understanding of electromagnetism's fundamental nature. Every magnet we've ever encountered, from the humble refrigerator magnet to Earth's own polar fields, has two poles, a north and a south. Cut a magnet in half and you don't isolate a single pole, you simply create two new, smaller dipoles. This symmetry seems absolute, woven into the fabric of electromagnetism itself. Yet theoretical physics whispers of an exception, a particle that defies this rule entirely. A magnetic monopole would be magnetism's answer to the electron, an isolated north or south pole, unattached to its opposite. Predicted by quantum theory but never conclusively observed, monopoles are cosmic phantoms that, if discovered, would force us to rewrite textbooks on electromagnetism and possibly reveal deep secrets about the universe's birth. The idea of magnetic monopoles first emerged not from experimental observation, but from mathematical necessity. In 1931, Paul Dirac demonstrated that quantum mechanics would be more symmetric and arguably more complete if monopoles existed. His calculations showed that their presence would neatly explain why electric charge in the universe appears quantized, coming only in discrete multiples of the electron's charge. Later, grand unified theories, GUTS, of particle physics predicted that monopoles should have been produced in staggering numbers during the universe's first moments of existence. As the primordial cosmos cooled and the fundamental forces separated, topological defects in spacetime structure analogous to cracks forming in ice could have frozen into existence as monopoles. These wouldn't be ordinary particles but incredibly massive relics, possibly as heavy as 10 to the power of 16 times a proton's mass, carrying a quantized magnetic charge that would interact with magnetic fields the way electric charge interacts with electric fields. The existence of monopoles would revolutionize our understanding of fundamental forces. They would prove that electricity and magnetism are even more deeply symmetric than we thought, a unification that could support theories linking all forces of nature under a single framework. Their discovery might also explain why the universe contains so much more matter than antimatter. Some models suggest monopoles could have catalyzed proton decay in the early cosmos, tilting the balance toward matter's survival. Yet their absence is equally telling. The fact that we haven't detected monopoles, despite extensive searches in lunar rocks, cosmic rays, and particle accelerators, has forced physicists to reconsider aspects of cosmic inflation. Many theories now suggest the early universe underwent a period of exponential expansion so rapid that it diluted monopoles to near non-existence, leaving perhaps just a handful drifting through the cosmos today. Even more intriguing are the potential technological implications. If monopoles exist and could be isolated, they might enable entirely new forms of energy storage or computation. Some speculative designs for fusion reactors even suggest monopoles could help confine plasma more efficiently than magnetic fields alone. But for now, monopoles remain hypothetical, a ghostly prediction at the intersection of quantum theory and cosmology. Their discovery would be like finding a missing puzzle piece that forces us to reassemble the entire picture of reality. If monopoles are the universe's missing magnetic fragments, what other invisible forces might shape existence? Next, we'll delve into dark energy, the mysterious pressure accelerating the cosmos's expansion and perhaps the greatest enigma in modern cosmology. In the late 1990s, astronomers made a discovery that shattered our understanding of cosmic destiny. By measuring the light from distant supernovae, they found that the universe's expansion wasn't slowing down as everyone had assumed but accelerating. Something was actively working against gravity's pull, stretching the cosmos apart faster and faster with time. This inexplicable repulsive force came to be called dark energy, and today it remains the most profound mystery in cosmology. Dark energy appears to be a property of empty space itself, a kind of anti-gravity woven into the vacuum. If it continues unchecked, it could eventually tear apart galaxies, stars, and even atoms in a distant future known as the Big Rip. Yet despite accounting for nearly 70% of the universe's total energy, we have no idea what dark energy actually is. Einstein was the first to conceive of something like dark energy, though he later dismissed it as his greatest blunder. His cosmological constant, originally introduced to balance gravity and maintain a static universe, turned out to describe precisely the kind of repulsive force driving cosmic acceleration. Modern measurements suggest dark energy behaves like a constant energy density filling all of space uniformly. Unlike matter, which dilutes as the universe expands, dark energy appears to maintain its strength, meaning its influence grows as space itself grows. This leads to the counterintuitive reality that the emptier the universe becomes, the more powerfully dark energy pushes it apart. The simplest explanation is that dark energy is the intrinsic energy of the vacuum itself, what quantum field theory predicts as zero-point energy. But there's a problem. Theoretical estimates of this vacuum energy exceed observed dark energy by 120 orders of magnitude. This staggering discrepancy, called the cosmological constant problem, suggests we're missing something fundamental about how gravity and quantum fields interact. Dark energy forces us to confront existential questions about the universe's fate. If acceleration continues, billions of years from now, distant galaxies will vanish beyond an unreachable horizon as space expands faster than light can traverse it. The cosmos will grow cold and dark, with isolated islands of matter stranded in an ever-growing void. Alternative theories propose even stranger possibilities. Some suggest dark energy isn't constant but evolves over time, a field called quintessence that could eventually dissipate or reverse. Others speculate it might be an illusion caused by our three-dimensional perspective of a higher-dimensional universe. There are even fringe proposals that dark energy's apparent acceleration could be a sign we're embedded in a region of unusual density within a much larger multiverse. The mystery cuts to the core of physics itself. Dark energy's weakness compared to theoretical predictions might be a clue that we don't understand gravity's behavior at cosmic scales, or it could imply the existence of undiscovered particles or dimensions. Future telescopes like the ESA's Euclid mission aim to map dark energy's influence with unprecedented precision, potentially revealing whether it changes over time or space. For now, dark energy remains an enigma, an invisible, all-pervasive force sculpting the universe's destiny while eluding explanation. Its discovery reminded us that the cosmos is far stranger than we imagined, and that the greatest discoveries often come from seeing not what's there but what isn't. If dark energy is invisibly shaping the cosmos, what other unseen phenomena might lurk in the void? Next, we'll explore dark matter, the mysterious substance outweighing visible matter 5-1, whose gravitational grip holds galaxies together. In the 1930s, astronomer Fritz Zwicky noticed something peculiar about the Coma galaxy cluster. The visible mass of its stars and gas couldn't possibly account for how fast its galaxies were moving. They should have flown apart long ago. He proposed the existence of Dunkel Materie, dark matter, an invisible substance whose gravity held everything together. At the time, his idea was dismissed. Decades later, Vera Rubin's meticulous observations of spinning galaxies confirmed Zwicky's suspicion. Stars at the edges of galaxies rotated just as fast as those near the center, defying Newton's laws unless some unseen mass was anchoring them. Today, we know dark matter outweighs normal matter 5-1, weaving an invisible scaffold that guides the formation of galaxies and bends the fabric of spacetime itself. Yet after nearly a century of searching, we still don't know what it is. Dark matter's presence is felt only through its gravity. It doesn't emit, absorb, or reflect light, hence dark, and seems to interact with normal matter solely through the gravitational force. Its particles, if they are particles, must be extraordinarily stable, persisting nearly unchanged since the universe's first moments. Cosmological evidence suggests dark matter is cold, slow-moving compared to light speed, which allowed it to clump early in cosmic history, seeding the gravitational wells that later attracted normal matter to form galaxies. Computer simulations of the universe match observations only when dark matter is included. Without it, galaxies wouldn't exist in their current configurations. The leading theoretical candidate is a hypothetical particle called a WIMP, weakly interacting massive particle, which would have formed copiously in the early universe and could still drift through our solar system today. Other possibilities include axions, ultralight particles predicted by quantum chromodynamics, or even primordial black holes formed in the universe's first second. Dark matter's invisibility forces us to question the very nature of reality. We've mapped its distribution through gravitational lensing, the way its mass bends light from distant galaxies, revealing vast halos surrounding galaxies and filaments connecting cosmic structures. Yet despite its dominance, dark matter seems to inhabit a parallel reality, barely touching our own except through gravity. Some theories propose dark matter isn't completely inert. Certain galactic anomalies suggest it might interact weakly with itself, creating dark forces, or even dark atoms in a hidden sector of physics. Others speculate that dark matter could decay or annihilate, producing faint signals we might detect as gamma rays or neutrinos. The search for dark matter has led to extraordinary experiments. Detectors buried deep underground wait for rare collisions between dark matter particles and atomic nuclei. Particle colliders attempt to create dark matter in high-energy crashes. Telescopes scan the skies for indirect evidence of its interactions. So far, all have come up empty or produced ambiguous results that vanish under scrutiny. This persistent failure has prompted radical alternatives. Some physicists suggest dark matter doesn't exist at all, that instead, our theory of gravity, general relativity, requires modification on galactic scales. Modified Newtonian dynamics, MOND, proposes adjusting gravity's equations to explain galactic rotations without invisible matter. But MOND struggles to explain all observations, particularly the bullet cluster where colliding galaxies clearly show gravity's source divorced from visible matter. Dark matter's mystery underscores how little we know about the universe's true composition. Solving it could reveal entirely new particles, forces, or dimensions, or force us to rewrite the laws of physics themselves. If dark matter is the unseen hand shaping cosmic structure, what other invisible phenomena might govern reality's deepest layers? Next, we'll examine quantum entanglement, a phenomenon Einstein called spooky action at a distance, where particles instantaneously influence each other across vast reaches of space. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper highlighting what they saw as a fatal flaw in quantum mechanics. They described a thought experiment where two particles could become so deeply linked that measuring one would instantly determine the state of the other no matter how far apart they were. To Einstein, this spooky action at a distance violated relativity's cosmic speed limit and proved quantum theory was incomplete. Decades later, experiments proved this entanglement was real. Particles born from the same quantum event remain mysteriously connected, their fates intertwined across light years as if space and time were mere suggestions. This phenomenon isn't just a laboratory curiosity, it may undergird the very fabric of spacetime itself, suggesting that separateness is an illusion and that the universe is fundamentally non-local at its core. Quantum entanglement occurs when particles interact in a way that their quantum states become inseparable. For example, two electrons created together might enter a superposition where their spins are undetermined yet perfectly correlated. Measure one as spin up, and the other instantly becomes spin down, even if it's on the other side of the galaxy. This isn't mere statistical correlation. Experiments have ruled out hidden variables that might predetermine the particle's states. The most famous tests by physicist John Bell in the 1960s and subsequent experiments by Alain Aspect and others confirmed that entangled particles exhibit correlations that classical physics cannot explain. The universe appears to maintain a silent, instantaneous connection between them, one that doesn't diminish with distance. Crucially, this connection can't transmit information faster than light. While the measurement of one particle affects its partner instantaneously, the outcome is random. You can't control what state you'll find, so no message can be sent. This preserves relativity's speed limit while still allowing for what Einstein called spooky coordination. Entanglement forces us to confront profound questions about the nature of reality. At the quantum level, the universe seems to operate as an indivisible whole, where particles share a hidden unity that transcends space and time. Some interpretations suggest that all particles that have ever interacted remain subtly linked in a vast, invisible web, meaning the entire universe might be built upon a foundation of entanglement. This has practical implications. Quantum technologies like unhackable quantum cryptography and ultra-powerful quantum computers rely on entanglement to perform tasks impossible for classical devices. Some theories even propose that spacetime itself emerges from a deeper network of entangled quantum information, that what we perceive as the distance between stars is really a reflection of how entangled particles share, or don't share, quantum states. The phenomenon also raises philosophical quandaries. If measurement determines reality at the quantum level, does consciousness play a role in shaping the universe? Or is entanglement simply revealing a mathematical structure deeper than our intuitive notions of locality? The answers could redefine our understanding of existence itself. If entanglement binds particles across space, could similar connections thread through time itself? Next, we'll explore temporal entanglement, where quantum links might defy not just distance but the arrow of causality. Imagine two particles so deeply linked that measuring one not only determines the state of its partner across space but across time. What if the act of observing a particle today could retroactively influence the state of another particle in the past? This is the mind-warping premise of temporal entanglement, a phenomenon where quantum correlations transcend not just distance, but the conventional flow of cause and effect. At first glance, the idea seems to violate our most basic intuitions about time. Yet quantum mechanics has never been constrained by human intuition. Recent experiments suggest that entanglement might indeed persist across time, creating correlations that challenge our understanding of temporal order itself. If confirmed, this would mean the universe at its most fundamental level doesn't distinguish between past and future as sharply as we perceive. Temporal entanglement builds upon standard quantum entanglement but introduces a radical twist. The entangled particles exist at different times. In conventional entanglement, two particles created together remain correlated in space. But in temporal entanglement, a particle could become entangled with another particle's future or past state. The mathematics allows for this. Quantum states can evolve in ways that entangle not just across space but across spacetime. Experiments with photons have demonstrated this by entangling a photon with itself at a later time, essentially creating a quantum link between its past and future states. Other proposals suggest that particles could be entangled with others that no longer exist, meaning a measurement today could influence the outcome of a measurement that technically already happened. This doesn't necessarily imply sending signals to the past. Quantum randomness still prevents controllable communication, but it does suggest that at the quantum level, time may be more fluid than we thought. If temporal entanglement is real, it forces us to reconsider the nature of causality. Does the future influence the past at the quantum level? Or is our perception of time as a one-way flow simply an emergent property of the macroscopic world, while the quantum realm operates outside it? Some interpretations suggest that temporal entanglement supports a block universe view, where past, present, and future are equally real, entangled across time like a single, unchanging structure. Others propose that quantum mechanics might allow for limited forms of retrocausality, where future events subtly shape past probabilities without violating overall causality. Practically, temporal entanglement could revolutionize quantum computing. If quantum states can be entangled across time, it might enable new ways to store and retrieve quantum information, or even create self-correcting systems where future measurements protect past states from decoherence. But the deepest implication is philosophical. Temporal entanglement hints that time itself may be a construct that emerges from deeper quantum relationships. Just as space loses meaning for spatially entangled particles, time might lose its strict ordering for temporally entangled ones. The universe, it seems, keeps its own time, and it doesn't always follow our clocks. If quantum connections can thread through time, what does that mean for free will and determinism? Next, we'll examine superdeterminism, a controversial theory suggesting that all our choices, even the quantum ones, might be predetermined from the dawn of the universe. Imagine every choice you believe you've made, every thought that felt like yours, every moment of hesitation or certainty was not truly yours at all, but the inevitable result of a chain of causes stretching back to the universe's first instant. This is the unsettling heart of superdeterminism, a radical reinterpretation of quantum mechanics that does away with randomness, free will, and even the illusion of independence between observer and observed. Unlike classical determinism, which was dismantled by quantum uncertainty, superdeterminism proposes that what we call random quantum events only appear unpredictable because we are blind to the deeper connections that bind everything together. In this view, the universe operates as a single, unbroken system where every measurement, every decision, and every quantum fluctuation was preordained from the dawn of time. It is a theory so extreme that most physicists dismiss it, not because the math forbids it, but because it erases the very notion of agency, reducing human consciousness to a spectator in a cosmic play scripted 13.8 billion years ago. Superdeterminism emerges as a stark solution to quantum mechanics' strangest puzzles. At its core, it challenges the assumption that experimenters can make truly free choices about how to measure quantum systems. Instead, it suggests that the experimenter's decisions are subtly but inexorably linked to the particles they study, part of the same web of causation that determines the experiment's outcome. This idea upends conventional interpretations of quantum entanglement. In standard quantum mechanics, measuring one entangled particle instantly influences its partner, no matter how far apart they are, a phenomenon Einstein famously dismissed as spooky action at a distance. But superdeterminism dissolves the spookiness by proposing that the particles and the experimenter's choices were always correlated, their fates intertwined since the beginning of time. There is no faster-than-light influence, only a universe so deeply interconnected that separateness is an illusion. The implications ripple outward. If superdeterminism is correct, then quantum randomness is a mirage, a reflection of our ignorance, not true indeterminacy. The unpredictability of a radioactive atom's decay, the apparent free will of a human mind, even the flutter of a butterfly's wings would all be threads in a tapestry woven at the Big Bang. The philosophical weight of superdeterminism is staggering. It undermines not just quantum theory's conventional interpretations, but the foundations of human experience. If all our choices are predetermined, then free will is a cruel trick of biology, a convincing simulation run by a universe that has already written every line of its own story. Science itself becomes paradoxical. How could we trust our conclusions about reality if the very act of forming them was predetermined? Critics argue that superdeterminism is unfalsifiable, a theory that, by its nature, cannot be tested, since any experiment designed to challenge it would itself be part of the predetermined sequence. Others reject it on aesthetic grounds, unwilling to abandon the intuition that we are more than passive witnesses to a cosmic script. Yet the theory persists because it offers a brutal simplicity. Without invoking parallel worlds, collapsing wave functions, or conscious observers, it claims to resolve quantum paradoxes by declaring them illusions. Some versions even suggest that superdeterminism could emerge from a deeper theory of quantum gravity, where spacetime itself encodes these hidden connections. The debate forces us to confront profound questions about the nature of reality. Is randomness essential for free will, or could free will exist even in a deterministic universe if we are part of the deterministic process? Does science require the possibility of true choice, or is it just another predetermined phenomenon? Superdeterminism offers no comforting answers, only the cold suggestion that the universe might be a clockwork machine, and we are merely gears in its mechanism. If the universe is a predetermined tapestry, what does that mean for time itself? Next, we'll explore externalism, the view that past, present, and future are equally real, fixed, and unchanging in a timeless block universe. We experience time as an unstoppable current, a relentless flow that carries us from what was, through what is, toward what will be. But what if this is nothing more than an illusion of consciousness? What if every moment that ever was or will be exists with equal reality, frozen in an unchanging cosmic tapestry? This is the radical proposition of externalism, the philosophical view that past, present, and future are equally real, and that the passage of time is just a trick of human perception. In this view, the universe is not unfolding, it simply is, a four-dimensional block where your birth, your death, and every moment in between exist eternally in spacetime. Your childhood isn't gone, it's still out there, as real as this instant, just at different coordinates in the cosmic fabric. This isn't science fiction, it's the natural conclusion of Einstein's relativity, where time loses its privileged status and becomes just another dimension through which we move. Externalism emerges from Einstein's revolutionary insight that time and space are interwoven into a single continuum spacetime. In relativity, there is no universal now. What one observer perceives as present, another moving at high velocity might see as past or future. This shatters the common-sense notion of an objective present moment moving through time. The block universe model takes this further, proposing that all moments in time exist with equal reality, much like all points in space exist simultaneously. Your fifth birthday party isn't gone, it persists eternally in the spacetime continuum, just as Paris continues to exist even when you're not there. The flow of time becomes a psychological phenomenon, not a fundamental feature of reality. This view is supported by the equations of general relativity, which treat time as a dimension where all events are fixed. From this perspective, the Big Bang isn't an event that happened, it's a location in spacetime, just as real today as it was 13.8 billion years ago. Externalism forces us to confront profound questions about existence and identity. If all moments are equally real, does free will have any meaning? Are our choices truly ours, or are we simply following a path already laid out in spacetime? Some philosophers argue that free will can still exist in this framework. Our consciousness is simply experiencing the timeline in sequence, making genuine decisions at each point. The theory also transforms how we think about death. In the block universe, your entire life exists eternally. Your first steps, your proudest achievements, your final breath are all equally real. This offers a strange comfort. In some sense, we never truly cease to be, any more than a movie ceases to exist when it reaches the final scene. Modern physics continues to grapple with externalism's implications. Quantum mechanics, with its apparent indeterminacy, seems at odds with the idea of a fixed future. Some interpretations reconcile this by suggesting all possible quantum outcomes do occur in different branches of a multiverse, each forming its own block universe. If time is an illusion and all moments exist eternally, what does this mean for the beginning of everything? Next, we'll examine the no-boundary proposal, where even the Big Bang loses its status as the absolute beginning of time. For centuries, humanity has grappled with the ultimate question. What came before the beginning? The Big Bang theory gives us a cosmic origin story, but it leaves the most profound mystery untouched. What, if anything, preceded that singularity? What if the question itself is flawed? What if the universe never had a true beginning at all? This is the radical proposition of the no-boundary proposal, a theory developed by Stephen Hawking and James Hartle that reimagines the birth of the cosmos. In this view, the Big Bang was not an explosion from nothingness, but a smooth transition, a bending of spacetime so complete that the very concept of before loses all meaning. Time, in this model, behaves like a dimension that gradually becomes space at the universe's origin, forming a closed surface without edges, without boundaries, and without a singular starting point. The no-boundary proposal emerges from the marriage of quantum mechanics and general relativity. In classical cosmology, the Big Bang appears as a singularity, a point of infinite density where the laws of physics break down. But Hawking and Hartle proposed that quantum effects would blur this singularity, much as quantum uncertainty prevents particles from having perfectly defined positions. Their mathematical model describes the early universe using imaginary time, a mathematical construct where time behaves like a spatial dimension. In this framework, the universe's origin resembles the Earth's south pole. There is no edge or boundary, just a point where all lines of longitude converge. Asking what came before the Big Bang becomes as meaningless as asking what lies south of the South Pole. This quantum smoothing creates a finite but unbounded spacetime, a self-contained cosmos that needs no external cause or creator. The universe would have emerged from a quantum fluctuation not in pre-existing space, but as space itself, with time crystallizing into existence as the cosmos expanded. The no-boundary proposal reshapes our understanding of existence itself. If correct, it eliminates the need for a first cause, offering a scientific alternative to theological creation narratives. The universe wouldn't be created, it would simply be self-contained and self-explanatory. This has profound consequences for the arrow of time. In the no-boundary scenario, entropy would start low simply because that's the only way a smooth, boundaryless universe can form, explaining why time appears to flow in one direction without invoking special initial conditions. The theory also suggests our universe may be just one among many in a quantum multiverse, each with different physical constants emerging from their own no-boundary origins. Some versions of the proposal even allow for the possibility that universes could nucleate inside black holes, creating a fractal cascade of cosmic births. Yet the no-boundary proposal remains controversial. Some physicists argue it requires untestable assumptions about quantum gravity. Others note that recent work in string theory and loop quantum gravity has proposed competing models of the Big Bang. But its central insight that the universe may have no beginning because it has no boundary continues to challenge our deepest assumptions about existence. If the universe needs no beginning, might it also have no end? Next, we'll explore the cosmic resurrection hypothesis, where the death of our universe could seed the birth of another. In the unfathomably distant future, our universe will face its ultimate fate, a cold, dark expanse where the last stars have burned out, black holes have evaporated, and even atoms themselves begin to decay. It is the heat death, the end of all thermodynamic possibility, where time itself loses meaning in an eternal freeze. But what if this cosmic death is not an ending but a transformation? What if the universe carries within it the seeds of its own rebirth? This is the essence of the cosmic resurrection hypothesis, a daring proposition that our dying universe could give rise to a new one not through divine intervention or external creation, but through the inherent physics of the void itself. Like a phoenix rising from its own ashes, reality might be cyclical, with each death birthing a new beginning through quantum resurrection or gravitational rebirth. The idea of cosmic rebirth takes several forms in theoretical physics. One version, rooted in quantum fluctuations, suggests that even in the vacuum of a heat-dead universe, random quantum events could eventually spawn a new Big Bang. Given infinite time, the quantum vacuum might spontaneously generate a bubble of false energy that inflates into a new spacetime. Another approach emerges from loop quantum cosmology, where the collapse of our universe could bounce, rather than end in a singularity, the crushing gravity of contraction reversing into expansion as spacetime rebounds into a new cycle. Perhaps the most radical version comes from black hole cosmology, which proposes that the singularity inside every black hole may be the birth of a new universe, with our own cosmos potentially having formed this way. In this view, universes reproduce like cosmic cells, with black holes as their birthing channels. If cosmic resurrection is possible, it transforms our understanding of time from a linear progression to an endless cycle. The constants of nature, the strengths of forces, the masses of particles might be slightly reshuffled in each iteration, creating an evolutionary pressure where universes capable of producing black holes or lasting long enough for life to emerge become statistically dominant. This could provide an elegant solution to fine-tuning. We find ourselves in a universe with life-friendly constants not because of design, but because endless cycles have statistically selected for them. Each resurrection would be a cosmic roll of the dice, with habitable universes eventually emerging through sheer probability across eternity. The hypothesis also offers a profound existential perspective. Civilizations arising in future cosmic cycles might find relics of previous universes encoded in the background radiation or fundamental constants, clues that they are part of an infinite sequence. Some theories even suggest information from our universe could bleed through to the next via black hole singularities, making cosmic death not an erasure but a transformation. Yet significant challenges remain. Current physics cannot confirm whether quantum fluctuations could truly birth a new cosmos from absolute emptiness, or whether the bounce scenario avoids hidden singularities. The ideas dwell in the realm of theoretical speculation, awaiting new mathematics or unexpected observations that could lend them weight. But the mere possibility reshapes humanity's place in the cosmos. We may not be inhabitants of a single linear universe, but participants in an eternal cycle where endings are beginnings, and death is just another word for rebirth. If universes can be reborn, might they also be shaped by unseen forces from beyond? Next, we'll examine shadow matter, a hypothetical mirror to our reality that could be interwoven with the very fabric of our existence. Imagine an entire universe existing alongside our own, not in some distant parallel dimension, but right here, interwoven with the very fabric of reality we inhabit. A world where stars burn with invisible light, where civilizations might rise and fall unseen, where matter obeys its own hidden physics, forever undetectable except through the faintest gravitational whisper. This is the haunting possibility of shadow matter, a theoretical form of existence predicted by some of the most advanced theories in physics. While dark matter remains mysterious, shadow matter presents an even more radical idea: not just invisible particles, but an entire mirror reality that shares our space while remaining forever beyond our perception. It is a concept that stretches the boundaries of what we consider real, suggesting that everything we know might be just one half of a far grander cosmic duality. Shadow matter emerges from the deepest symmetries in theoretical physics. Just as every particle we know has corresponding antiparticles, some theories suggest there could be entire sectors of particles that interact only with their own versions of the fundamental forces. These shadow particles would have their own electromagnetism, their own nuclear interactions, a complete parallel physics operating alongside ours. In string theory, this idea takes on even more profound dimensions. Our observable universe might be a four-dimensional brane, floating in a higher dimensional space, with other branes, other universes existing mere millimeters away in dimensions we cannot perceive. Under the right conditions, matter on these branes would be completely invisible to us, feeling only its own forces, yet still contributing gravitationally to the structure of our cosmos. The most striking consequence? These shadow particles could form shadow atoms, shadow molecules, even shadow planets and stars, all occupying the same space as our own matter, yet passing through it like ghosts. If shadow matter exists, it could solve some of cosmology's most stubborn puzzles. The missing satellite galaxies predicted by dark matter simulations might instead be shadow matter halos, unseen but exerting gravitational influence. Certain anomalies in cosmic microwave background radiation could be echoes of interactions between our matter and shadow matter in the early universe. Even more astonishing is the possibility of shadow complexity. Shadow stars could fuse shadow elements in their cores. Shadow planets might develop shadow chemistry. Shadow life could have evolved entirely independently of our own. Some theories even propose that dark matter itself could be the remnant of a long-dead shadow universe, a fossilized imprint of a parallel reality that burned out eons ago. Yet for all its theoretical elegance, shadow matter remains elusive. No experiment has yet detected its presence, and some versions of the theory suggest it may be fundamentally undetectable except through the subtlest gravitational distortions. Particle colliders like the Large Hadron Collider have searched for evidence of extra dimensions and shadow particles, but so far the universe has kept its secrets. Still, the idea persists, a tantalizing whisper that reality may be far richer than we perceive. If shadow matter is real, then everything we see, everything we are, might exist alongside an entire unseen cosmos, forever just beyond the veil of our perception. If unseen matter could form hidden worlds, what about unseen dimensions? Next, we'll explore Brane cosmology, where our universe may be just one membrane floating in a higher dimensional void. We perceive our world in 3 dimensions of space and one of time, a firm, tangible reality bounded by length, width, and depth. But what if this is merely an illusion? What if our entire universe is nothing more than a thin membrane, a brain floating within a higher dimensional space we cannot see or touch? This is the startling premise of Brane cosmology, a theory that reimagines the cosmos not as an isolated expanse, but as one of many possible universes drifting through a grander, hidden dimensionality. In this view, the Big Bang might have been the aftermath of a collision between our brain and another. Gravity could be leaking into dimensions beyond our own, and the very laws of physics we take as fundamental could be local phenomena unique to our membrane reality. It is a vision of existence that makes even the most far-fetched science fiction seem provincial by comparison. Brane cosmology emerges from string theory's requirement that the universe has more than the familiar 4 dimensions, perhaps 10 or 11 in total. These extra dimensions, the theory suggests, are either compacted into sizes far smaller than an atom or are inaccessible because our entire universe is trapped on a 4-dimensional brane within a higher dimensional bulk. In this framework, the particles and forces we know might be bound to our brane like waves to the surface of an ocean. Gravity, however, could be different, a force not confined to any one brane, but capable of spilling into the bulk. This would explain why gravity is so weak compared to other fundamental forces. Its strength is diluted as it leaks into dimensions beyond our perception. Some versions of the theory propose that the Big Bang was triggered when our brane collided with another, releasing immense energy that inflated into the universe we know. These collisions could be cyclical, with branes periodically drawing together and rebounding in an endless cycle of cosmic destruction and rebirth. If Brane cosmology is correct, it would revolutionize our understanding of reality's architecture. Other branes, other universes could exist millimeters away from us in higher dimensions, completely invisible yet potentially hosting their own forms of matter, energy, and even life. The laws of physics in these branes might differ radically from our own, with alternate constants, forces, and perhaps even different numbers of observable dimensions. This could provide testable predictions. If gravity does leak into the bulk, microscopic black holes might form at lower energies than expected in particle colliders. Gravitational waves from brane collisions could imprint faint patterns on the cosmic microwave background. Some theorists even suggest that dark matter could be ordinary matter trapped on a nearby brane, its gravity bleeding into ours. Philosophically, Brane cosmology forces us to confront the possibility that our universe is not special, but one of countless membranes in an unfathomably vast higher dimensional ensemble. The fine-tuning of our physical constants might be an illusion. We simply inhabit one of the rare branes where conditions allow for complexity in life. Yet for all its grandeur, the theory remains speculative. No direct evidence for extra dimensions or other branes has been found, and some formulations may be inherently untestable. But as a vision of reality's potential richness, it stands as one of the most awe-inspiring ideas in modern physics, a reminder that the truth of the cosmos may be far stranger than we dare imagine. If our universe is a membrane floating in higher dimensions, what happens when these dimensions unravel? Next, we'll examine false vacuum decay, a quantum catastrophe that could rewrite reality in an instant. Imagine if the very fabric of reality was built on unstable ground, not metaphorically, but in the most literal sense possible. What if the universe as we know it exists in a precarious quantum state, like a glass perched on the edge of a table, and all it would take is the slightest nudge to send it shattering into an entirely new form of existence? This is the existential threat posed by false vacuum decay, a theoretical scenario in which the universe's fundamental quantum fields could suddenly collapse into a more stable state, rewriting the laws of physics in an instant and erasing everything we know in an unstoppable wave of annihilation. The process would be silent, invisible, and utterly inescapable. One moment, the universe would function as it always has. The next, a bubble of true vacuum would expand at the speed of light, overriding reality with new physical constants where atoms, stars, and life as we understand it could no longer exist. It is, in essence, the ultimate cosmic reset button, one that could be triggered at any moment without warning. According to quantum field theory, what we perceive as empty space is not truly empty, but seething with energy, the so-called vacuum state. This vacuum could exist in a false configuration, temporarily stable but not at the lowest possible energy level, the true vacuum. Like a ball resting in a shallow valley on a mountainside, it persists in this state only because it hasn't been given enough energy to roll down into the deeper valley below. A quantum fluctuation could provide that push. If even a single point in space tunneled through the energy barrier into the true vacuum, it would create a bubble of reconfigured physics. The walls of this bubble would expand in all directions at light speed, rewriting the fundamental forces as they go. The strong nuclear force might cease binding atomic nuclei, electromagnetism could dissolve, making chemistry impossible. The universe would not end in fire or ice, but in something far stranger, a transformation so total that not even the concept of destruction would survive. The most unsettling aspect of false vacuum decay is that it could already be underway. A bubble of true vacuum might have formed in some distant galaxy billions of years ago, and its lightspeed expansion would give no warning before it reached us. The laws of physics would change so completely that we wouldn't just die, and everything we know would cease to be viable structures in the new vacuum. Some theories suggest this may have already happened elsewhere in the multiverse, with each bubble universe hosting different physical laws. Our universe's seemingly fine-tuned constants might simply be the ones that survived in this particular bubble. Others propose that high-energy particle collisions could, in theory, trigger local vacuum decay, though the energies required are far beyond anything our technology can produce. Yet there is a strange beauty in this fragility. The fact that our universe has persisted for 13.8 billion years without collapsing suggests that either the false vacuum is extraordinarily stable, or we exist in the brief window before inevitable decay. Some calculations indicate the process could take longer than the current age of the universe to occur spontaneously, but on cosmic timescales, even a 1% chance per billion years adds up to near certainty over eternity. False vacuum decay forces us to confront the transience of existence at the most fundamental level. Not just life, not just stars, but the very laws of physics might be temporary, a fleeting configuration in an endless quantum landscape. If the universe's fundamental state could catastrophically change, might time itself be subject to similar instability? Next, we'll explore time crystal structures that break time symmetry, creating order that persists eternally without energy. For centuries, the dream of perpetual motion was dismissed as a fantasy, a violation of thermodynamics' ironclad laws. Yet in 2012, Nobel laureate Frank Wilczek proposed something that seemed to flirt with just such an impossibility: time crystals, structures that oscillate indefinitely without energy input, breaking time symmetry just as ordinary crystals break spatial symmetry. The idea was initially met with skepticism, but by 2017, experimentalists had created time crystals in the lab using chains of ytterbium ions and superconducting qubits. These bizarre quantum systems don't produce energy, they don't violate thermodynamics, but they do something almost as strange. They lock into an eternal rhythm, a heartbeat of quantum coherence that persists even in the universe's eventual heat death. Time crystals are phases of matter that spontaneously break time translation symmetry, meaning their structure repeats not in space but in time. Imagine a clock that ticks forever without being wound, or a ring of quantum particles that perpetually flip their spins in a fixed sequence without energy loss. This behavior emerges in carefully tuned quantum systems driven by periodic forces. Unlike conventional matter, which settles into equilibrium, time crystals resist this stabilization. Their components synchronize into a rhythm distinct from the driving frequency, like a pendulum that swings at half the rate you push it. This subharmonic response is the hallmark of a discrete time crystal. The phenomenon relies on many-body localization, where quantum interference prevents a system from thermalizing. Particles become trapped in a labyrinth of their own quantum states, unable to distribute energy evenly and thus preserving their ordered oscillations indefinitely. Time crystals challenge our understanding of equilibrium. They suggest that certain quantum systems can evade thermal death through complexity rather than energy input, a revelation that could rewrite how we think about information preservation in quantum computers. Some theorists speculate that time crystals might exist naturally in extreme cosmic environments, perhaps in the dense cores of neutron stars or as relics of the early universe's phase transitions. Others propose using them as precision sensors or as fault-tolerant quantum memory. Most profoundly, time crystals hint that time itself may have more complex phases than we imagined. If matter can lock into eternal rhythms even as the universe cools toward absolute zero, then the arrow of time may host structures as rich and varied as spatial crystals, a hidden dimensionality to temporal order waiting to be explored. If quantum systems can create eternal temporal order, could similar effects shape the cosmos? Next, we'll examine cosmic inflation's quantum seeds, how microscopic fluctuations grew into galaxies. The universe, at its grandest scales, is a tapestry of galaxies, clusters, and vast cosmic voids, a web of matter stretching across billions of light-years. Yet this immense structure may have originated from the tiniest of beginnings. Quantum fluctuations smaller than an atom, amplified to cosmic proportions in the first moments after the Big Bang. These microscopic ripples in spacetime, born from the raw uncertainty of quantum mechanics, were stretched to astronomical sizes during the period of cosmic inflation. What began as fleeting quantum jitters became the gravitational seeds around which all galaxies, stars, and planets eventually formed. The universe we see today with its intricate cosmic architecture may owe its existence to these primordial quantum whispers. According to quantum field theory, empty space is never truly still. At scales far smaller than atoms, particles and antiparticles flicker in and out of existence, their fleeting presence governed by Heisenberg's uncertainty principle. During the universe's inflationary phase, a period of exponential expansion in the first fraction of a second, these quantum fluctuations were stretched from subatomic to cosmic sizes. As inflation expanded space faster than light, tiny density variations in the quantum foam became frozen into the fabric of spacetime. When inflation ended, these variations imprinted themselves on the distribution of matter and energy, creating slightly denser regions where gravity would eventually pull matter together into galaxies and clusters. The cosmic microwave background, the afterglow of the Big Bang, bears the faint fingerprint of these primordial ripples, a snapshot of quantum uncertainty writ large across the sky. The fact that quantum fluctuations shape the cosmos has profound consequences. Without them, the universe might have remained perfectly smooth, a featureless sea of particles with no galaxies, no stars, and no planets. The same randomness that governs the behavior of electrons in an atom may have determined where galaxies would form billions of years later. This connection between the quantum and the cosmic also raises deep questions about the nature of reality. If quantum fluctuations were truly random, then the large-scale structure of the universe, including our own Milky Way, could be the result of pure chance. Some interpretations suggest that other regions of the universe, far beyond our observable horizon, may have entirely different arrangements of matter, shaped by different quantum outcomes. Moreover, the precise pattern of these fluctuations provides critical evidence for cosmic inflation. The distribution of galaxies and the subtle temperature variations in the cosmic microwave background match predictions made by inflationary models, lending support to the idea that the universe underwent this exponential expansion. Yet mysteries remain. Why did inflation start? What drove it to end? And are there traces of even earlier quantum phenomena buried deeper in the fabric of spacetime? If quantum fluctuations shaped the universe, could they also govern its ultimate fate? Next, we'll explore vacuum metastability, the precarious quantum balance that might one day rewrite reality itself. We like to imagine the laws of physics as eternal and unchanging fixed rules that have governed the universe since the beginning and will continue to do so forever. But what if the fundamental constants that dictate reality's behavior are not absolute? What if they are merely temporary, the result of our universe being trapped in a fragile state that could, at any moment, collapse into something entirely different? This is the unsettling possibility of vacuum metastability, a quantum phenomenon where the vacuum of space itself might be hanging in a precarious balance, waiting to fall into a more stable configuration that would rewrite the fabric of existence. The implications are staggering. If such a transition were to occur, it would propagate outward at the speed of light, erasing all known physics in its wake. Atoms would disintegrate, forces would unravel, and the universe as we know it would cease to function. The unsettling truth is that this could already be happening somewhere in the cosmos, and by the time we saw it coming, it would already be too late. In quantum field theory, the vacuum is not simply empty space, it is a seething, energetic medium where particles flicker in and out of existence. The properties of this vacuum determine the fundamental constants of nature: the strength of gravity, the mass of electrons, the speed of light. But the vacuum's current state may not be the most stable one possible. Instead, it could be metastable, like a ball perched on a hill, seemingly stable until a slight nudge sends it tumbling into a lower energy valley. This idea arises from the Higgs field, which gives particles their mass. Calculations suggest that the Higgs current energy state might not be the lowest possible. If a quantum fluctuation were to push it into a more stable configuration, the change would propagate outward in an expanding bubble. Within this new vacuum, the laws of physics would be different, perhaps so different that matter as we know it could no longer exist. The most disturbing aspect of vacuum decay is its inevitability. If our universe is indeed in a metastable state, then given infinite time, a transition becomes statistically certain. Some estimates suggest the probability is vanishingly small on human timescales, but over trillions of years, the odds shift toward inevitability. Yet there is a strange duality to this idea. While it presents an existential threat, it also offers a possible explanation for why our universe's constants are so finely tuned for life. If countless vacuum states exist in the multiverse, most of them hostile to complexity, then we naturally find ourselves in one of the rare, long-lived metastable bubbles where physics permits our existence. Experimental searches for vacuum instability focus on precise measurements of the Higgs boson's mass and the top quark's properties, data that could indicate how close we are to the edge of stability. So far, results suggest our vacuum is likely metastable but with an expected lifetime far exceeding the current age of the universe. Still, the possibility lingers, a reminder that reality as we know it might be more fragile than it appears, balanced on a knife's edge between existence and annihilation. If the vacuum's instability threatens the universe's future, could its origins also hold clues to deeper mysteries? Next, we'll delve into holographic entropy, the idea that all information in the cosmos might be encoded on its boundary. Imagine if every event within the cosmos, every star that burns, every thought that forms, every atom that collides was not truly happening in three-dimensional space, but was instead a projection of information stored on a distant, two-dimensional surface. This is the radical proposition of the holographic principle, a theory suggesting that our perceived three-dimensional reality might be nothing more than a hologram, an illusion generated by quantum data encoded at the universe's boundaries. The idea seems like science fiction, yet it emerges from some of the most profound puzzles in theoretical physics, particularly the nature of black holes and the limits of information in the universe. If correct, it would mean that everything we see, touch, and experience is a kind of cosmic mirage, a shadow cast by deeper, more fundamental processes unfolding at the edges of spacetime. The holographic principle was first proposed in the context of black hole thermodynamics. When matter falls into a black hole, its information appears to be lost, a violation of quantum mechanics, which states that information must always be preserved. However, physicist Gerard T. Hooft and later Leonard Susskind suggested that the information isn't destroyed but is instead encoded on the black hole's event horizon, the two-dimensional boundary from which nothing can escape. This led to a staggering generalization. If a black hole's entire interior can be described by information on its surface, could the same be true for the universe? The holographic principle posits that all the information contained within any region of space can be represented as data stored on that region's boundary, meaning our three-dimensional reality might be a projection of a two-dimensional source code at the cosmic edge. In this view, the universe operates like a hologram, where a lower dimensional surface contains all the necessary information to reconstruct the higher dimensional whole. The ADS/CFT correspondence, a concrete realization of this idea in string theory, demonstrates that a five-dimensional anti-de Sitter space can be perfectly described by a four-dimensional conformal field theory at its boundary, a mathematical hint that holography might be fundamental to reality's structure. If the holographic principle is true, it would revolutionize our understanding of space, time, and information. The three-dimensional world we experience would be an emergent phenomenon, with the true real physics happening at the universe's edges. This could solve long-standing problems in quantum gravity by providing a framework where gravity in higher dimensions emerges from quantum field theories in lower dimensions. The principle also challenges our intuitive notions of locality, the idea that objects interact only with their immediate surroundings. In a holographic universe, seemingly distant events might be deeply connected at the informational level, with changes on the boundary instantly affecting the interior in ways that defy classical intuition. Some interpretations even suggest that the holographic principle could explain consciousness itself, that our perception of a three-dimensional world is a kind of rendering by the brain, interpreting two-dimensional data into a volumetric experience. While this remains speculative, it underscores how deeply the holographic metaphor could reshape not just physics, but our understanding of existence itself. Yet mysteries remain. The holographic principle works elegantly in certain mathematical models, but applying it to our real, expanding universe is far more complex. If the cosmos is holographic, where exactly is its boundary? Is it the cosmic horizon set by the speed of light and expansion? Or is the principle more abstract, a statement about information density rather than a literal surface? For now, the holographic principle stands as one of the most tantalizing ideas in theoretical physics, a hint that reality's deepest truths might not lie within the space we inhabit, but on the edges we cannot see. If the universe is a hologram, what generates the projection? Next, we'll explore quantum entanglement and spacetime, how the fabric of reality itself may be woven from subatomic connections. At the heart of reality lies a paradox. The smoother and more continuous the universe appears to our senses, the more fragmented and probabilistic it becomes at the quantum scale. Yet what if this fragmentation is not a flaw in nature's design, but the very foundation of spacetime itself? Emerging theories suggest that quantum entanglement, the spooky action at a distance, that troubled Einstein, might be the invisible thread stitching together the cosmos. The implications are profound. Rather than spacetime being the fixed stage upon which particles interact, It may instead emerge from deeper quantum connections, a holographic tapestry woven from countless entangled particles. In this view, the geometry of the universe, the force of gravity, even the flow of time itself could all be collective illusions arising from a hidden network of quantum correlations. The idea builds upon two revolutionary insights. First, black hole thermodynamics revealed that the information capacity of any region of space is proportional not to its volume, but to its surface area, a hint that reality might be fundamentally two-dimensional, with a third dimension emerging from quantum data processing. Second, experiments confirmed that entangled particles remain instantaneously connected regardless of distance, violating classical notions of locality while preserving causality. Combining these observations, physicists like Mark van Ramsdonk and Brian Swingle have proposed that spacetime itself condenses from quantum entanglement. Imagine two particles entangled in a quantum system. Their shared connection creates a microscopic bridge of spacetime between them. Multiply this effect across countless entangled particles, and the fabric of the universe emerges like a cosmic neural network, with each quantum link contributing to the geometry we perceive as gravity and dimension. This framework, sometimes called ER equals EPR, after two landmark physics papers, suggests that Einstein-Rosen bridges, wormholes, and quantum entanglement may be two faces of the same phenomenon, one described by general relativity, the other by quantum mechanics. A wormhole's spatial connection could simply be entanglement made geometrically manifest. If spacetime is indeed built from entanglement, it would provide the missing link unifying quantum mechanics with general relativity. Gravity would no longer be a fundamental force, but a thermodynamic consequence of quantum information scrambling, like how temperature emerges from atomic motion. The Big Bang might represent the moment when universal entanglement first froze into classical spacetime structure. This perspective also reshapes our understanding of black holes. When matter falls in, its information isn't lost but becomes encoded in surface-level quantum entanglements, preserving information while dissolving the very spacetime within. Some models even suggest our universe could be the interior of a higher-dimensional black hole, its physics holographically projected from surface entanglement. Most radically, if entanglement creates spacetime, then manipulating quantum links could theoretically engineer spacetime itself, opening possibilities for metric engineering or even simulating universes in quantum computers. The flow of time might correspond to the gradual building of new entanglement connections across the cosmos. Yet profound challenges remain. Current quantum gravity models only demonstrate this emergence in highly simplified universes. We lack experimental proof that entanglement scales up to create spacetime's curvature. And the theory struggles to explain why we perceive a smooth, classical reality when its foundation is presumably fractured and probabilistic. As we conclude this journey through quantum mysteries, we're left with a humbling realization. The deeper we probe reality, the more it dissolves into questions. From the holographic principle to vacuum decay, from entanglement to emergent spacetime, each discovery peels back a layer only to reveal greater complexity beneath. The universe may be stranger than fiction not because it defies logic, but because it operates on a logic we're only beginning to decipher. These quantum enigmas aren't just academic curiosities, they're clues to the ultimate nature of existence, written in a code we're slowly learning to read. As you drift into sleep tonight, consider that the very space around you, the passage of time, even the stability of matter might all be quantum illusions, temporary patterns in an infinite dance of probability. The greatest mystery isn't any one paradox, but the fact that this dance gives rise to conscious beings capable of witnessing it at all. Thank you for exploring these cosmic riddles with us. If these ideas resonated, consider subscribing for more journeys to the edge of understanding. Sweet dreams, and remember, reality is almost certainly weirder than you imagine. We've journeyed through the most baffling mysteries of quantum physics, realities that shift when observed, parallel universes branching endlessly, particles communicating instantaneously across space and time. Each of these ideas challenges our deepest assumptions about existence. Perhaps the most humbling lesson is this: the universe is far stranger than we can imagine. And yet, here we are, tiny conscious beings trying to make sense of it all. If these mysteries captivated you as much as they fascinate us, consider subscribing for more deep dives into the unknown. Leave a comment below what quantum concept blew your mind the most. Do you think reality is truly as bizarre as these theories suggest? Thank you for joining us on this journey through the quantum unknown. Like, share, and sleep well knowing that the universe is far more mysterious than any dream. Good night.